Hello, everybody. Hey, this is a continuation of our lecture on angular momentum, but I would like to get a few things sort of straightened out, kind of a bit of a review. So we have, as we've seen in the past, we've got linear and angular analogies. For example, distance in a linear sense is the angle or theta in the angular sense, okay? Same thing with velocity and angular velocity, acceleration and angular acceleration. So we could call that linear velocity or linear acceleration. Now, when it comes to the relationship between the linear and the angular, it's usually going to be R. Okay, there's going to be a relationship between the radius. But let's talk about force. Now, in a linear force, we know that's just a push or a pull. And we can think of that as just mass times acceleration, which we'll talk about. Now, in the angular sense, we're going to have torque, which is R cross F. And we know in our last lecture that this cross product was rather complicated, right? And it had to do with matrices. But remember that torque is really just force times radius, okay? That's force times radius as long as the force and radius are perpendicular. We've talked about this. So we could also think of this as F R sine theta, which is giving us that perpendicular component. So if we end up looking at that and going back at that lecture, that sign, when you do those cross products from the matrices, certainly involve the sign. So you can kind of go back and review that. Now, a lot of times this torque is going to be easier than that cross product. It's going to be easier than that cross product. And because usually the force and the radius are in the same plane. So if we have a force and a radius in the same plane, which we can certainly always make it that way, unless the axes are superimposed upon us, okay? So for example, if we have kind of a force this way and kind of a radius this way, right? Even though they could be in three-dimensional space, right? My two lines emanating from the same place is going to define a plane. And then we don't have to worry about having the answer in that IJK format. Just realize that the direction of the torque is going to be perpendicular to that plane, So I like to think of it as when you turn a screw, okay? So when you turn a screw, so your plane is going to be, let's say, this way, but the screw is going to move in and out, okay? And so that's kind of a way of me thinking about that torque is going perpendicular to that plane, okay? It is also going to be related to angular momentum, which we talked about, and linear momentum, remember, is just mass times velocity. And so angular momentum, okay, is defined by R cross P, also being a vector, right? So this has those same attributes as the cross product, which we talked about last week. So this can kind of get complicated, but we can also just summarize it down in a similar way here. We're going to have mv, which is our momentum, times our radius, times the sine of the angle, or just that perpendicular, okay? So there's a lot of relationships here, but again, the direction of our angular momentum is going to be perpendicular to our plane. And if we have something, let's say, in the XY or the IJ plane, then either our torque or angular momentum is going to be in the positive K or the negative K. And you may remember from last week's lecture is that we can use the right-hand rule, okay? And we can take the radius would be one, which would be one of the vectors. So we take our right-hand fingers and we go in the direction of our first vector in that cross product, and then we bend them towards the other one. So if we have, for example, a vector A, okay, and a vector B, then if we have A cross B, okay, then we would take our hands right here and we would go up in that direction of A, and now we're going to curl our hands towards the B. And since it's our right hand, my thumb would be sticking out perpendicular out of the plane, and therefore we would call that positive. We'd call that positive K. And if we have the reverse, if we have B cross A, okay, then we kind of take our right hand going up the B and curl it towards the A, and now my thumb would be pointing into the board, which we call negative, okay? So using the right-hand rule will help us to determine which direction it goes, and not necessarily relying on that cross product. Okay, so let's talk about impulse, okay? And this would be linear impulse, okay? And that would be force times time. And so when we get over to the angular, we kind of have that same thing. Torque times time is going to give us a change in momentum. Force times time is going to give us a change in momentum. So you might remember the definition of impulse, force times time, but it is equal to a change in momentum. So we have some similarities there. Now, when we're talking about all of these things, essentially what we want to do is, when we're talking about forces or torques, okay, we're really talking about when we add them all together, right? So when we add a force vector or torque vectors, that will add up. That will add up to be one vector, right? So we can end up having that all in that case. So if you look at dividing both sides by t, we can see that the sum of the torques is going to give us the change in momentum over time. And we can think of that as the derivative with respect to time of that momentum. Okay, so let's talk about this thing right here, because at mvr sine theta, we can see that, and it's not really that obvious, is that if you have an object going in a straight line, it is going to have a constant momentum as long as the velocity stays the same, which seems weird. How can you have a straight, something going straight that's going to have an angular momentum? Now, it's going to be the case, but you have to have a point of reference, okay, or a line of axes, okay? So if we have a mass times velocity, right, so we have a momentum that's cruising along in this direction. Now, if I want to know what is that angular momentum, with respect to this line right here, okay, then this right here, okay, that perpendicular would be the r. So the L would equal to mvr if that is at a right angle. Well, what if it's not at a right angle, right? So what if we take a point right here, okay, and it is moving at this point right here to the right, okay? So it's going to have an mv. Now this, okay, this is the radius, right? And this is the angle. And now we go back to this and we see mvr sine theta. Well, what is r sine theta? Well, r sine theta is this r right here, right? So it's the same thing. Now, what if we change, and now we're a little bit further along, and now we're going to have this, okay? So now we're gonna have another radius, okay? But we're also gonna have another angle. And when we look at that angular momentum is equaling to mvr sine theta, now we're gonna have, this would be a different angle, this would be mvr sine phi. And again, what is the sine of that angle with respect to the hypotenuse? And it would be this r right here. So anything going in a straight line with respect to some point or some line that is parallel to that momentum will have angular momentum. Okay, now if we have this MV going parallel to that axis or to that pivot point or axis point, then we can see that the r would be 0, and we would not have any angular momentum with respect to that point. Okay, so that seems a little bit odd there, that something can go straight and it's going to have angular momentum. So what I would like to do here is just do an example of something that's going to review a bunch of stuff and very introductorily talk about the angular momentum. Okay, so let's say that we're going to have two disks. Okay, so we're going to have a disk that's going to have a radius of 10 centimeters. Okay, and we are going to superimpose that. We're going to place that. Let's see if I can do a better circle. Okay, and basically we have two disks. We have two disks that are superimposed upon it, right? So if we were looking at a side view, okay, we would have something less. Think of a pulley system, right? And we're going to say that the inner radius is 10 centimeters, and let's say it's 2 kilograms. And now this bigger disc is going to have a radius of 25 centimeters. And let's say it is going to be 5 kilograms. Okay. So now now we're going to apply some torques, right? So we're going to apply a torque this way. Let's say that is 20 newtons. And let's say that that's going to be at an angle of 30 degrees. And we're going to have a 5 newtons acting straight down. And then let's say that we're going to have a 30 Newton force that's acting directly to the right. Okay, so my first question would be something like, what is the sum? What is the sum of the torques? What is the sum of the torques? Now, you guys, we can go back and look at torques, which is going to be FR sine theta. And we would have, for example, we'll call this F1, F2, and F3. So the torque 1 would be equal to F1 R sine theta. Now, whenever you have a rope that is going from a spool or a cylinder, okay, this angle right there is irrelevant because it's going to be coming from the radius. So this would not be sine 30. It would be sine 90. And sine of 90 is going to give us 1. So we're going to have 20 here times 0.25 times 1. Okay, so our first torque, is going to be 5, and those units are Newton meters. Okay, so torque 2 is going to be 5 times 0.1 times the sine of 90. Okay, and that's going to equal to 0.5 meter newtons. And now our torque 3 is going to be 30 times 0.25, and that is going to be 7.5 meter newtons. Okay, so it looks like when we add these up that we're going to get 13 meter newtons as the sum of the torques. But that is not, you guys, that is not the right answer, because we have torques that are going in different directions. Okay, so 4 directions when we're talking about circular, we talked about this before, is going to be clockwise and counterclockwise. So if we say to clockwise is positive, right, then we're going to say plus, minus, minus. And now we can see that if we go plus, minus, minus, we're going to have an answer of -3 from the clockwise direction, -3 from the clockwise direction, which is obviously going to be +3 in the counterclockwise direction. Okay, so obviously they are going to be the opposite. Okay, now, you guys, if we have, this is going to be our second question, if our initial angular velocity is 0, then what is our angular acceleration? Okay, now this actually is irrelevant. This could be anything, and we can still figure out what our initial angular momentum is going to be. Okay, so remember that torque, and we do not have this written up here, okay, but torque here is also equal to I alpha. Torque is also equal to I alpha. So remember that our linear force is equal to ma, so we have an angular analogy to that. And remember that our angular equivalent, our angular analogy to mass is the moment of inertia. And that moment of inertia is going to be the sum of the mr squares, okay, which could also be equal to the integral of r squared dm, okay. But mostly where we're going to get that is going to be on page 278. 278 is going to give us a list of formulas in order to calculate what those moment of inertia is. Now, you guys, we already know what the torque is, right? So when we go back to this one, okay, torque is equal to I alpha. So if we divide both sides by A, we're going to have torque. Now, our torque, we already found out, was 3 meter newtons, which would be in the counterclockwise direction. And now we're going to do a quick calculation over here to calculate our moment of inertia. So we essentially have 2 solid disks here, and on page 278, the equation for a solid disk for calculating the moment of inertia is 1/2 mr squared. Okay, so for our smaller one, we're going to have 1/2 of 2 times 0.1 squared. That's going to give us 0.01. Okay, and then our second one is going to be 1/2 times 5 times 0.25 squared. So 1/4 squared is 1/16, and half of 1/16 is 1/32, and so we're going to say 5 divided by 32, and that's going to be 0.156. Okay, 0.156. And so when we add those together, we're going to get 0.157. And now if we are looking for the units here, we're going to have kilogram meter squared. So this would be kilogram meter squared. So we can say 0.157 kilogram meter squared, okay? And then we're going to have our alpha here, and 0.157. So we're going to get 19. Okay, so our alpha here is going to equal to 19. Now, you guys, if we look at this, the units here, one of our meters canceled out. So remember, a Newton is a kilogram meter per second squared. So the other meter cancels out, kilogram meter squared, and we're left with 19 per second squared. Okay, and remember that even though radians is a dimensionless unit, we kind of put it in there to talk about how the angle would be changing with respect to time squared. Okay, all right, so this would be our second answer. So we might even call another answer. We needed to calculate what our initial moment of inertia was. Okay, so let's get another couple questions answered here, and same diagram. And now let's say after 5 seconds, if our initial velocity was 0, then what is our final velocity, angular velocity, after 5 seconds? Okay, so now we're going to go back and use the kinematic equations. And if we think about it, the kinematic equation that we're going to use is the second one, which is omega final is equal to omega initial plus alpha t. We know that that goes away, so we're going to have 19 times 5. And that 19 times 5 is going to give us 95, and that's going to be radians per second. So we could then ask, what is the angular momentum? What is the angular momentum? So angular momentum, which is going to be equal to I omega, okay, which would be equal to 0.157 times 19. And we're going to get 3. So our angular momentum at the end of this 5 seconds is going to be 3. And that is going to be kilogram meter squared per second. So now if we look here, angular momentum is equal to mv, so we have that linear analogy. So now when we go to angular, we're going to have those same relationship, and that is I, which is the angular analogy to mass, and omega, which is the angular analogy to velocity. Okay, and one thing that we are going to be exploring here, and let's talk about this up here. We're going to have I omega is also equal to our angular momentum. And just as linear momentum is conserved, angular momentum is also conserved. Okay, so we can say I initial omega initial would equal to I final omega final. Okay, so we will talk more about that, and until next time, this is our done with our